Okay, good evening. Welcome back. Today is an important lecture. I will just start by recalling a few things and then even recall the last 5 minutes because I understand a bit better now. So what we did in the first part of last week, we discussed some examples in 2D, and I will recall why 2D is a bit special. So we look at one example, which is this Lotka-Volterra equation, and the second equation is called Yenot's equation. And for this second example, we have seen, and I emphasize it, that the notion of observable is important. Observable is a function which has a certain property. It's a function on the space which has a certain property when you look at it along the evolution. And we end up with the fact that in some cases of Leonard's equation, there exists a unique periodic orbit, and all other orbits converge to it, except the fixed point. That's why I put a star. Of course, if it is a fixed point, it will not converge to anything else. But all other orbits except the fixed point will move to this periodic orbit. So we had an example. What is special in 2 dimensions, it is this Jordan curve theorem, which says if you take a closed curve which does not cross, then it separates the plane in 2 parts, the interior of the curve and the exterior. This is true in 2 dimensions. There is no analog with a curve in 3 dimensions or higher. And this theorem allows us to describe completely what happens or all the limit sets in R2. And this is this Poincaré-Bennigsen theorem, which lists 3 possible cases. Either you have one fixed point or a periodic orbit, or finitely many fixed points and some open orbits between them. And there are 2 pictures in the notes which represent this second or this third case. All right. So this is all for 2 dimensions. And then we move to any dimension. So we cannot use this Jordan curve theorem anymore. Still, our framework is the same. We consider a dynamical system, which is a continuous time. The space is inside Rn, and we assume that it's a solution or it's a flow generated by a first-order differential system. We assume it's complete, which means all trajectories are well defined for all t. So we can take a limit t goes to plus infinity or t goes to minus infinity. And we introduce a new object. So instead of just looking at the forward or the backward orbit of one point, so remember this gamma is you fix a point and you look either at the trajectories of this point when t goes to plus infinity or when t goes to minus infinity. Now we consider the same thing, but for a set. So for a set X, we can consider all trajectories defined by this set when t goes to plus infinity or t goes to minus infinity. This is not so interesting. I mean, there is nothing special. It's just the union of all individual trajectories. But the limit set is more interesting. So this was a limit set for 1 point. Now we can consider, I gave the definition of the limit set for X, a subset of M. And it turned out that this is usually bigger than just a union. Why? And I try to explain it. It's because you can, when you define this set, you can jump from one orbit to another one. So instead of just considering all orbits which start inside capital X, when I define the limit point, I can jump from one orbit to another one, and it gives us more freedom. And we have seen on an example what it means. So we have seen that this is, in this example, it's a strict inclusion. We don't have equality. Then in order to better understand this concept, my final aim is to define what is an attracting set, an attractor. I recall the notion of distance between either a point on a set or between 2 sets. And I gave one definition of what is called a stable and unstable set for gamma. So I take lambda, sorry. I take lambda invariant set, and I'm looking at all points in M which approach lambda as t goes to either plus infinity or minus infinity. So the distance between lambda and the trajectory is going to be 0 in the limit t goes to plus or minus infinity. So this is the last object I introduced. I want to add a few things about this. Probably I already mentioned a few things last week, but I want to make it more clear this time. So remember, the final aim in this section is to understand what is a attracting set and what is an attractor. I need to give a definition of an attractor. So I continue from this definition. So what we observe, and this is quite clear, the set lambda itself belongs to W plus or minus of lambda. Why? Because it's an invariant set, so the distance between lambda and this point is 0 because you stay inside. So this is quite clear. And what is the use? Or we can wonder, or maybe this is what I didn't explain last time. We can wonder what is the use of this W plus or minus of lambda. Last time we have seen an example where we had this. We had two fixed points, minus 1, 0, 1, 0, and the point 0, 0, and we have seen that everything is attracted toward these points. But we started with one ball. So the idea with this set is, instead of fixing an arbitrary ball, we are looking for the biggest set which is going to converge to lambda. If we look at it, it's going to be the set of all points which are approaching lambda when the flow goes to plus infinity or minus infinity. So the idea is really, instead of just starting with an arbitrary one, I want to take the biggest one, what it means. So this is the idea of this W plus minus. We fix an invariant set, for example, this one, or maybe just one point. And I'm looking for all points which are approaching it when t goes to infinity or t goes to minus infinity. So that's the idea of this set. But however, not all lambda or all of these sets will be interesting. We will concentrate on some of them, and this justifies a new definition. So an invariant set, lambda, is attracting. So this is a new definition. It's attracting if the stable set, so the stable set is a W plus of lambda is an open setting. If you are first here, you maybe don't see why open sets are so important, but in many subjects, an open set is important, and the main difference is what is, in Rn, the definition of an open set. An open set has a property that if you pick any point, you can draw a small ball which is inside. That's the main property of an open set. If you take the boundary, so now I take the closure, so I take also the boundary, we don't have this property. If I draw a small ball, the small is not inside. It's partially inside, partially outside. Open set has a property that no matter where you are, you can be very close to the boundary, you can draw a small ball around which is still inside. That's why open sets are so important. So we say that this invariant set is attracting if this guy, so in a sense, a set of all points which converge to it is open. And we will see an example. And of course, it's an open set which contains this one. Because, as we have seen, it's inside. So it's an open set in which somewhere you have your initial set lambda. So this is called an attracting set, or we give this definition. And in this case, if W plus is open, we say that W plus of lambda is either its domain, the domain of lambda, or its basin of attraction. So remember, we use this only if this W plus is open. This is an important property. Okay, now you can wonder, oh, okay, we have a nice definition, but how do we find attracting sets? So how do we find lambda which have this property? So we can get attracting set with the following notion, with what is called trapping sets. So I have to define what is a trapping set. If you have any question, you can ask me at any time. Heavydo is not here, so I need somebody else to ask questions. Okay, so again, now I'm wondering, how can I find these attracting sets? And the good notion is the notion of trapping set. So what is a trapping set? It's not so difficult, but it's interesting. The trapping set is an open. It's an open connected. Connected means made of one part. You can go through it just by staying inside the set. Unbounded. Bounded, I think we understand. It means it's inside a box. It's an open, connected, unbounded set X inside M such that, well, the main property is the following one. Okay, so I need to explain what it means. What is X bar is precisely the closure. So remember, I start with the open set. X is an open set. Now X over line means I take also the closure. So I take the boundary. And this notion of trapping is quite nice because what it means the evolution of the boundary goes inside X as soon as t is bigger than 0. So it means the boundary is not usually at the beginning, but as soon as you let the flow go, these points are going inside. So the boundary immediately after, once t is bigger than 0, the boundary is inside. So through the flow, it contracts. That's why it's called trapping. It traps even the boundary. So this is a definition of a trapping set. It's a kind of contraction, if you have this in mind. And so so now I explain why this notion of trapping set is important for defining attracting sets. It's for the following reasons. It's an easy lemma. For any trapping set X, W plus or minus of X is non-empty. It's non-empty, so there is something inside. It's closed. It's invariant. It's bounded. It's connected. And in addition, it is attracting. And which is the main property I'm looking for. So if we summarize, as I said, W plus minus, this W allows us to look for a big set which is converging to an invariant one. How do we know that it's attracting in the sense that this W plus is open? We have the answer. If you find a trapping set, then its limit set is attracting. it's not completely easy to put all pieces together, but I think now on the blackboard we have everything. Do you have any question? So this notion of trapping set, it's quite natural. And whenever you have a trapping set, its limit set has a property that it's attracting. However, we are not always completely happy with this, because in this example, this ball of radius slightly larger than 1 is a trapping set. It has this property. But we have seen that its limit is this closed interval. But if you look carefully, this entire set is not very interesting, because what is really attracting in this set is only these 2 points. These are really the attracting one. In a sense, if you look carefully, this part is not what we would like to say that it's attracting. It is, according to this definition, but why we get this, if you remember, this part is because we can jump from orbits to orbits. And in fact, here we have a speed essentially 0, close to the fixed point 0. So at last, when I define an attractor, I want to eliminate precisely some parts. So we will see. And as I said, in this example, there is one part which is not very nice. And it's for the following reason. There is a lemma, which I find interesting. So it's another result related to this one, which says the following. For any trapping set, which probably I call it trapping region. Okay, in the note I call it region, but it's the same as set. For any trapping region X and any fixed point X inside W plus of omega of X, I will make a picture, one has so I have to explain, but this is a problem I mentioned. So again, I recall the problem on this example we have seen last week. Suppose it's symmetric. Symmetric. So now we have a nice picture in the note, by the way. What is the meaning? I told you if I take the ball as we did last week, so this is capital X, the limit set is this entire closed set. But in this entire closed set, we have one fixed point, this one. And what is the unstable set for this fixed point? It's W minus, so it is a set of points which were close to it in the past. So if the dynamic is like this, on these horizontal orbits, everything is moving in this direction. So it means all points here in the past were close to this one. You have to go backward in time. So it means this entire line, not with the endpoint, but this entire line here this is called the unstable set for, in this case, it is 0, 0. So all these points in the past, if you look when the evolution is going to positive time or to plus infinity, they are moving to this attracting point. So it means in the past, they are going close to this one. So these two open intervals are in fact the unstable set for 0, 0. And this is a general result. Whenever you have a trapping region, you can look at its limit point, its limit set. If in this limit set you have a fixed point, this is the case here, its unstable set, also its entire unstable set belongs to this one. And we would like to eliminate this. There are different ways to eliminate this situation, but the one which I'm going to present is one which is often used. So we need one more notion, and we will see that with this final notion, we have exactly what we need. So I know it's not easy. If you have any question, there is no stupid question, just ask. Sorry? I need somebody to say something. So please ask a question. You are. We have plenty of excellent students in this room, so you can ask questions. Okay. So what is the last notion I need to introduce? You know it well. It's the notion of topologically transitive. This is a notion which can be found in many contexts. I will try to explain what it is. So again, my aim is in this, okay, it's only on one example that I'm trying to justify, but my aim is to finally get only these 2 points in this example as attracting points. The rest, they are not really attracting. They are simply, these lines are due to this fixed point and to the zero velocity that you have around this fixed point. So what is the last definition? As I said, it's topologically transitive, which is probably new for most of you, but it's a nice notion. So we consider a closed and invariant set, lambda. This set is called topologically transitive. This is a complicated name, but it's called topologically transitive if for any u and I take two subsets, open subsets of lambda, one has. And you will see that it's a very nice notion, 5t u intersection with b or some. What does it mean? Whenever you see a new definition, you should try to make a picture. This very simple picture, but let's try to do it. We have, let's call this closed and invariant, or closed, usually I make it as a box. So my convention is whenever I draw a closed set, it looks like this. But that's not important. But because it's closed, I do the boundary. It's invariant. It means if you take a point inside, it will stay inside. It will not leave. This is a notion of invariant. Any point stay inside under the evolution. And what is a statement? It's topologically transitive if take any subset U and V. This is U and this is V inside, and let them evolve. So I need to let this evolve, no matter what it does. But the statement is that after some time, it will meet V. So the intersection will not be empty. It's a kind of mixing. This, no matter which U and V you take, you let one of them evolve, it's going to touch the other one. This is the notion of topologically transitive. So it's really a notion of mixing, because I can take another V here. Through the evolution, I will partially go through this set. So it means this image of U is going to spread essentially everywhere. But be careful, orbits cannot cross. So I cannot make something like this. This is not allowed. Remember, I cannot do this because it would mean two orbits are crossing. So this is not allowed. So, but still it has to visit all places. So it has to go, I don't know how, but it has to go like this. So this is a nice notion of topologically transitive. Take two sets, let one evolve, the intersection will be non-empty. You can mix these two sets. As I said, this notion of topologically transitive play a big role in dynamical system, but also in others subjects. Why? Now let's look again at this example. Why is this closed? This interval with a boundary is a closed subset, and it's invariant. If you are inside, you stay inside. Why is it not topologically invariant? Oh, sorry, topologically transitive. This property is not satisfied by this because, look, if I take a U, I take an interval here, and I take, this is my U. If I take an interval V here, they will never meet. U is going to stay inside this. This is a fixed point. They cannot cross it. So it means U is going to stay inside. Probably it will even move towards this point. V will move towards this point, but they will never meet. So this is not a topologically transitive set. Is it clear? Yes.
We just only take the x-axis in one dimension. It is a closed set which has some open sets. But if you look at the two-dimensional x-like plane, then it's a closed set without any open sets. So if we consider it with respect to this two-dimensional plane, then the definition is...
No, but the evolution is, if you take any point inside this, I mean, it's a closed set, and any open subset in this is just an interval, an open interval. It's with a restricted topology. So in this case, an open set is an open set inside omega. And the restricted topology is you start, you are right, with the open set in R2, which is a ball, for example. But when you take its restriction to your set, you get just an open interval. Now, it's not completely easy, but that's it. Now, there is a remark which is also not trivial, and I gave a link. A closed and invariant subset of Rn is topologically transitive. If it contains a dense orbit. So I have to explain this. But be careful, this statement is true in Rn. It's not true in all settings. So what is the notion of a dense orbit? It means you start just with one point and you visit essentially everything. And why is it dense? It's dense if, again, take a point, any point, take any small ball of any radius, the trajectory has to go through this ball at one point. This is a notion of a dense trajectory. And yeah, you can see these two notions are very much related, but be careful, they are not equivalent. So it depends on the setting. but I put a link where it's explained. But here the statement is, if you have a dense orbit, so if this orbit goes everywhere up to a size, up to a distance epsilon, then you have this mixing or this topologically transitive property. And now I can give you the right notion of attractor. Let me keep the picture for a second. So the final notion of what is an attractor, a closed, invariant, attracting, and topologically transitive subset of M is called an attractor. So this is the final definition for this section. So closed, we know what it is. Invariant, it means all trajectories stay inside. Attracting, we have defined what it is. You have to look back at what it means. It means its basin of attraction is an open set. And now we have seen this notion of topologically transitive. So if you have these four properties, you call this set an attractor. And this is a good notion for dynamical system. And so on our example, which subset satisfies this? We have only 2 points, either this point, which is -1, 0, or this point, which is 1, 0. Yeah, 1, 0. So we could think about this closed interval, but as we have seen, it's not topologically transitive. You can think about also this point, 0, 0. It is topologically transitive because a point, there is nothing to check. But if you check, it's not attracting. Why it's not attracting? Because it's the set of points which converge to it, just to this point, consists of these two lines. And these two lines are not open in R2. And the same if you think about this closed interval 0, 1, because this closed interval from 0 to 1 is closed invariant, but again, it's not and it is topologically transit. Yes, it is topologically transitive because the point here, no, it is topologically transitive, but it's not attracting because the set of points which converge to this closed interval is a half space, including this vertical line, and this half space is not open. So there is no choice. On this example, the only subset which are closed invariant, attracting, and topologically transitive are either this point or this point. So we have now, for this example, only 2 attractors, which are these 2 points. Okay, but of course, we wouldn't build the entire theory just on one example. So it means that this notion of topologically transitive is also important for other examples.
The points are the only attractors in this example, right?
Yeah.
But how would we define subsets of a point?
There is no subset of a point.
It's itself.
Yeah, it's itself.
Oh.
That's why the notion of topologically transitive for one point, you don't have to check anything. It's automatically satisfied. Yeah, you're right. Okay, so I finished this section. Do you have any question? So the next one is an example. So this is 5.2. probably, or 6.2. 6.2. It's a famous one. You have certainly seen, no, it's just, you have certainly seen some pictures, and I put one in the note. I'm not going to do it on the blackboard. It's called the Lorentz attractor, and it's surprisingly simple. And why is it interesting? Because it's in 3 dimensions. So we don't have this theorem of Poincaré-Bendixson, which tell us that we have only 3 things, 3 possible limit sets. Indeed, in this example, the limit set is more interesting and more complicated. So I will not write everything about this, but let me sketch what happens. So we consider the following dynamical system. So we have 3 constants inside. So it's a 3-dimensional problem, but in addition, we have 3 constants. And just be careful. In the note, I wrote the t dependence, but here I don't write that. It's x of t, y of t, z of t. And as I said, we have 3 constants. We have sigma, we have r, and we have b, which are 3 constants bigger than 0. So it's a rather simple dynamical system. The first order derivative is this function of x, y, and z, and a constant here sigma, a constant here r, and a constant here z. B, sorry. There are just a few observations. You can easily find one solution and one symmetry of this problem. The symmetry is that if you consider the map x, y, z goes to minus x, minus y, z. So you change x and y into minus x and minus y, we get the same system. So it's invariant under this change. You can check if you then the derivative will also change its sign. Here it will change the sign of both. Here it will change the sign. This one will change its sign, this one as well, and this one as well, because z is constant. And this one would not change its sign. But here you would have a product of 2 minus sign, and this one will not change its sign. So it's invariant. And one solution, so this is a symmetry, and one solution, which is easy, is 0, 0, and z0 e minus bz, minus bt. I should put a trend, oh, I have this problem with t. Transpose. You can check this is a solution for any z0, because the first 2 lines would disappear, and you would have just derivative of z is minus b times z. This is a solution. So it means the vertical axis is given by these 3 orbits. You have a fixed point 0, and you have 2 orbits, one above for positive z, one for negative z, depending on z0. Now, what about 0, 0, 0? First, I consider for r. So r is always strictly positive, but smaller than 1. I'm claiming that 0, 0, 0, so the origin is a stable fixed point. And let's check it. Oh, it's a stable fixed point. So why is it a fixed point? Put 0 everywhere. You will see that your system is satisfied. If x, y, and z are 0, the derivative are 0. So it's a solution. Now, why is it stable? Remember, we can linearize a system around a fixed point and check what happens. And I will come back to this even in the next section. But if we linearize, so if we look, we consider, by the way, I can write this as f of x, y, t. The right-hand side is this f. So when I write, we can consider the Jacobian. So the Jacobian, I use this j for the function f at 0, 0, 0. Yeah, probably sometimes, no, okay. Sometimes 0, I consider the 0 in 3D. Sometimes I write the 3 coordinate. So we can consider the Jacobian at the point 0. If you're familiar with calculus 2, you can easily compute it. It makes minus, it's made of partial derivative evaluated at 0. Minus 1, 0. If you have not done calculus 2, you will learn this next semester. This is a Jacobian matrix. You take the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z, and you put it here, and you evaluate at 0, 0, 0. That's why some terms are 0. And then you need to compute the eigenvalue, the eigenvalues of this. It has eigenvalues. Okay. I have written these 3 eigenvalues in the notes. You can compute them. This is not difficult because the matrix is quite special. One is easy. It is this one. And then you need just to compute the eigenvalues related to this 2 by 2 matrix. And they are strictly negative. Negative. First, they are real and negative. And we have seen this in the linear case when eigenvalues are negative, strictly negative. When the eigenvalues are strictly negative, everything converges to 0, 0, 0. So this is something we have seen. And this is why it's a stable fixed point. It converges to 0, 0, 0. You can look at the corresponding theorem when you have a linear system with eigenvalues which are strictly negative, it converges to 0, 0, 0. But this is a local information. So it means in R3, a priori, I know only on a small domain like this. I know that any point in this domain would converge to 0, 0, 0. And by the way, in these eigenvalues, if you compute them, you will see that this condition R smaller than 1 is used. So this is why I put it. But now there is a slightly stronger statement. It turned out that I cannot use this argument for a point far away because I do a linearization. It's a local information. But with the notion of observables, we are going to see that all trajectories are indeed converging to 0. I cannot use this because this is local, but with what I'm going to present now, we will see that everything is converging to 0, still in this case, R smaller than 1. So what is the argument for this? It's again with the notion of observable. So we are going to define an observable and see that this observable is negative along the evolution. So we define one observable. It's a function L of x, y, z. Oh, welcome. So it's this function of x, y, and z given by this rx squared plus sigma y squared plus sigma z squared. You can almost recognize if r sigma were both 1, it would be the distance to the origin. Here, it's a kind of deformed distance because this is bigger than 0, this is bigger than 0. So it's a kind of distance, but we scale in some direction. But essentially, I can say a deformed deformed distance to 0, 0, 0. Why deform? Because of these parameters which are not 1, but that's it. So I consider this observable, and I'm going to, I consider let x of t, now I write it, y of t, z of t, or transpose, be a solution of the initial system. It's no more on the blackboard, but I wrote this system before, so I consider one solution of it, and I'm going to compute the derivative of this observable along the evolution. So I consider d of dt of L of x of t, y of t, z of t. It's not very difficult. You compute derivative of this. This is calculus 1. It's a composition of function because remember x is a function of t, so you would get 2 times r times x times x dot of t plus 2 times sigma times y dot of t plus 2 times sigma z dot of t. Then you replace x dot, y dot, and z dot by the system, and you end up with something which is negative. So again, or maybe I can write just what you get. So this derivative along the evolution is minus 2 sigma times r. So you need to compute something, but that's fine. So I wrote the t dependence at the end instead of x of t, y of t, and z of t. But what we observe, all terms are positive, but we have a minus sign before in the front. So it means this is negative. And remember, we are in the case when r is smaller than 1. That's why this term is also positive. This factor, with my assumption, it's positive. So we have a derivative which is negative, and we have seen that when we have an observable with a derivative along the evolution which has a specific sign, we can get something, and in this case, the conclusion is all points or all orbits converge to the origin. And now you can still wonder, why does it converge to the origin? Look, I told you it's a distance, and it's a deformed distance, but this distance has a negative derivative, so it means it's decreasing. And if the distance decreases, no matter if it is deformed or not, if the distance decreases, it means you are approaching the origin. So in this case, it's not an approximation as we did here with the Jacobian. It's really true for any x, y, z, for any orbit. If you start with one point and look at its evolution along, you look at its evolution, then the distance to the origin is decreasing. So it means it's converging to the origin. And it's even strictly, so it doesn't stop. So this is why observables, again, are so useful. They allow you to, by the way, it's not completely trivial to guess this. So it's often not easy to find an interesting observable. But if you are clever enough and if you feel the system, you might be able to construct an observable which has a meaning and which has a certain sign along the evolution. So again, we did 2 arguments. Locally, it's clear that it's 0 is attracting, so it's a stable fixed point, but it's even more general because all points are converging as long as R is strictly smaller than 1. Now, what happens for R bigger than 1? And here in the notes, I haven't written all the details. I haven't done my homework. I haven't checked everything. So if somebody is interested in this example, you can fill the details. And it's available at many places. I check in many books, you can find these things. I just copied some results. If somebody wants to check why, it's not so difficult, but it takes some time. So what happens for R bigger than 1? We have two new fixed points. So you can check that these are solutions, and these fixed points are given by plus or minus square root of b times r minus 1. This is the first coordinate. Second coordinate is the same, plus or minus b r minus 1. And third coordinate is r. This t is always for transpose. So these are two new fixed points. So now we have 3 fixed points. And you can study their stability. So study the stability of this fixed point locally. It's the same as here. You compute the Jacobian matrix at this fixed point. And you compute the eigenvalues. And you look at the eigenvalues. If the 3 eigenvalues are strictly negative, it means that it's a stable fixed point. If some of them are positive or negative, you need to be a bit careful. But it turns out, and this is where I just copied, these 2 points are stable, are asymptotically stable. So it means they attract asymptotically. And here there is something I don't understand. It's written for R between 1 and this 470 divided by 19. I have no idea where this number comes from. So you really need to do the computation. I don't know if it is a strict value. I mean, if the statement is no more true after this, or if you can still go a little bit, and this is only an approximation. So this is, if somebody wants to write a report, you need to study precisely the Jacobian matrix for this and try to understand. But again, it's written at many places, so it's probably standard, and I'm pretty sure that the computation I've written somewhere. But it would be nice to understand why this 470 by 19. And by the way, this is about 24 something. It's 2474 because it plays a role. So say it again?
Do you get a report by the 470 by 19?
Yeah, it would be a nice report if somebody gets this number.
I know.
But you have also to explain why. So you need to, but I think it's okay. No, I would be happy if somebody work on the detail for this. And what is the next thing I want to say? And again, here I will not write the detail on the blackboard. There is a general fact. We have seen that for r smaller than 1, all trajectories converge to 0. This is not true for r bigger than 1. But there is something which is true, is we have a trapping region. And I define it in the notes. There is a definition. It's a kind of ellipse or ellipsoid. There is a trapping region, and I explain what is a trapping region. Remember, it's a bounded and open region of R3. In this case, it's R3. So it's a bounded and open region of R3, such that if you look at its boundary, we have the following property. I just recall it. Phi of x1 closure, no, it's t first. T x1 closure is inside x1 for any t bigger than 0. This is a definition of trapping region I introduced before. So what I'm claiming is for any, I think this, yeah, for any R bigger than 0, this X1 is a trapping region. And this trapping region is defined in the node. So it means any point on its boundary would go inside. And we have seen, there was a lemma before, that trapping regions are interesting because I recall it. So there are two things which, or there are two facts. One, so X1 is a trapping region. This is the first thing. So the trapping region is mentioned there. So it implies that its limit set is invariant. No, is attracting. Sorry, is attracting. This was the main point. In the notion of attracting, I recall at the beginning. But we have, so this is already something interesting. And the second point is that we have more. In fact, with a suitable observable, which is defined in the note, with a suitable observable. All trajectories ends in X1. So it's about the same argument. What we show is that with this suitable observable, if we are outside, we will, at a certain point, we will go inside. It's again a notion of distance. There is a distance to an object which is inside. This distance is decreasing, and so it means you have to cross and enter this region X1. So it means don't try to solve all problems now. It means for this, for R arbitrary, this trapping region means we have an attracting set, which is its limit point or its limit set. And in addition, all trajectories outside end up in X1. So it means everything which is interesting is inside this domain. We don't really need to care about what is outside. Everything end up inside. So this is the main. So you can find a bit more, some additional information in the notes. And precisely, there is inside this. So now, depending on, so this is, I don't write the details, it's a bit annoying. So if I summarize what we have, so after this, we get, then if I call capital lambda the limit point of this X1 is so we have all the properties I mentioned before. So it's an attracting, it's bounded because it's inside this domain. It's connected. This is something we have seen before. It's closed. It's invariant set. This is all the things I already mentioned when I introduced trapping region, closed, invariant, bounded, connected, and attracting, and non-empty. And it turns out that this set is called, it's called the Lorentz attractor. And for some parameters, it is what is called a strange attractor. I haven't defined it so far, and I will not do it right now, but this is something we will still see what is means a strange attractor. You should complain about one thing. There is one thing I didn't prove. I think we don't. I didn't check, but I think we don't know. I mean, not only I've read something very quickly that in this, maybe you can check, but so indeed, according to the way I define an attractor, I should first check that it's topologically transitive, and it seems to me that I read it's not no. But still, people call it a Lorentz attractor. But yeah, according to the definition, or maybe I do a mistake, maybe it's proved, but. And for some parameters, it's even called strange attractor for some reason. I'm not sure that it's not for all parameters, but for some of them. All right, so I don't say much more than this. Maybe I will come back to this example in the last lecture, because who attended the class on data assimilation? You attended it? Anybody else? Okay, no. I gave a course on data assimilation, and there was an application to the Lorentz attractor, and it was a nice application. So maybe I will come back to it at the last lecture. How you can control the chaos, how you can control chaotic system. This was the aim of this work. Do you have any question? So again, if somebody wants to fill the details, understand how I define in the notes X and then X1 and why some inequalities are true, it would be a nice report. Okay. So we can move to the last section of this chapter about stability. So far we have seen stability around a fixed point. I will recall a few things. I will add a result about this. And we will also, maybe next week or maybe already today, see the stability. What means stability around a periodic orbit? Because in the Leonard's example, or Leonard's equation in 2 dimensions, we have seen that we have some periodic orbits. In this example, it was easy because all trajectories would converge to the periodic one. So it means this periodic orbit in 2 dimensions is attracting. But now if we have a periodic orbit in higher dimension, we can still have something periodic in higher dimension. It may happen that it's attracting or not, or it may depend in which direction. So you have, I will explain this, but in some directions it can be attracting, and in other direction it can be repulsing. So we are going to study the stability around the periodic orbit. So this section contains 2 things. So this is 6.3, stability. Around fixed point, we said already quite a lot. So first we start stability around a fixed point. So we consider, so we are still in the setting of a first order autonomous differential system, and we consider x0 a fixed point of the equation x dot of t is f of x of t. I consider a fixed point of this, and for simplicity, I assume x0 is 0. Why? You can always do it just translate your system. If you have a fixed point at one place, you just make a translation of your differential equation. You know, when you have a differential equation, you have in fact fixed an origin. Y is 0, 0, 0. You can move your origin to a different point. So if you have one fixed point, I can always do a translation and end up with this fixed point at 0, 0. There is no loss of generality in this. So I will assume that my fixed point is at 0. This is a 0 in Rn. Oh, it's a 0 in Rn. Sometimes I make it bold. Yeah.
Already kind of translation and what
We are in Rn. Yeah. No. This chapter, yes, I'm not cleaning. I'm in the most general setting. Sorry. Yeah. We are in the case of a dynamical system. R, it's a continuous time. M is inside Rn. And we have the flow generated by a first order differential equation. This chapter is in this setting. Yeah. No, okay. I don't consider something more complicated than this. So, yes. In this case, we can consider the linearization. So as I already mentioned, what is the linearization? It means we set A, which is a Jacobian matrix of F at 0 in the linear system. Which is X, this is a linear system, X dot is A X of T. This is a linear system. We studied this in chapter 2. So we have seen when we are in this framework, we have 3 subspaces. The 3 subspaces, I denote them by E, S, E, U, and E, C. This was defined in chapter 2. What is S stands for stable, U for unstable, and C was for critical, but apparently it's also called the center. They also call it the center. It depends a bit on the author. So we have these 3 subspaces, I just recall how we define them. We look at the Jordan normal form of this matrix. Then we look at the eigenvalues which have a positive real part, a negative real part, or a 0 real part. The one with a negative real part define this stable subspace. The one with a positive real part defines this unstable subspace. The one with a 0 real part defines this critical part. This was the way we define these 3 subspaces. And there is one situation which is easier than the other one, is when EC is 0. So the simplest situation, the simplest case, and the theorem I'm going to mention is in this case. Simplest case, EC is equal to just the subspace 0. It means no eigenvalue of A with real part 0. This is the simplest case. And in this case, we say that in this case, we say that x0 is a hyperbolic fixed point. This is a new word. So take any dynamical system of this form, find a fixed point. I put it at 0. Then we can define these three subspaces. And I just claiming, or this is a new definition, if this subspace related to eigenvalue of 0 real part, if this subspace is just 0, we say that this is a fixed point, which is hyperbolic. This is the best situation because you can already feel a little bit why. Think about the real line. 0 is very singular. It's a point, while all values which have a positive real part is much bigger, and all values which have a negative part is much bigger. 0 is just 1 point. So why is it better when there is no point, no eigenvalue with 0 real part? Is because if you do some perturbation theory, and whenever you study a problem, you often do some perturbation theory. If you are here and perturb a little bit, you are still inside this part. Or if you are here and you perturb a little bit your system, you are still around here. If you are at 0 and you perturb, everything can happen. You don't know what is going to happen. So it means you have more stability, you have more tools if you are in this part, or if you are in this part. And again, this is an open set. This one is an open set. I said already once, open sets are nice because exactly you have this freedom to construct a small ball. So hyperbolic systems are easier to study than when we have an eigenvalue with a 0 real part, because it's very unstable. So the next statement is precisely in the case of a hyperbolic system. It doesn't mean that we cannot study when we have a 0 eigenvalue or the 0 real part, but you have to be more flexible. You have to be more careful. So what is the theorem which I want to present? It's a full description of what happens close to a hyperbolic fixed point. So I consider f of class C1. So again, it's one differentiable, continuously differentiable. And M is a subset of Rn. So we are in this framework. I consider X. No, I suppose we assume 0 is a hyperbolic fixed point. Of this equation. So again, it means this is not a big assumption. It just means I have a fixed point and I move it so that it is at 0. If your fixed point is not at 0, you just move it to 0. So assume 0 is a hyperbolic point of this equation. I'm going to set A for this Jacobian matrix of F at 0, is above 0, and I define, and I use set phi for the flow. So the phi I have always used phi for the flow generated by this differential equation. So the phi I have always used. And what is the statement? So this is a framework. The statement is the following. There exists a function phi defined on an open set around 0, which is, it's a, I have written bicontinuous, bijective, and bicontinuous. So if what bijective, so let me draw a picture. Okay, I do it in 2D. We have, I do 2 copies of R2. I do it in 2 dimensions. So it means we have phi, which is defined on an open set around 0, which goes to another open set around 0. It's bijective, so it means you can come back. And it's bicontinuous, it means phi and phi minus 1 are continuous. This is a notion of bicontinuous. So you can only define it if the function is bijective. Otherwise, you don't have a phi minus 1. But I assume the function is bijective, so it has an inverse, and the inverse is continuous. So the statement is there exists a phi which look like this, such that, oh, yeah, I put hyperbolic fixed point, such that, so that phi of x is x plus h of x is h bounded. And this is not the most important thing. Phi times et. So I let you look at this and then we discuss. Yes. What does it mean? So the first line means this phi is, if we had no h, it would just be the identity. So if there is no h, it's just the identity function. So it means it's the identity plus something which is bounded. So it's small perturbation of identity. But the main point is this line. It says the flow around the point 0 can be written as, look, this is a linearized evolution. So it's a continuous deformation of the linearized evolution. So it means this flow is not so far from the linearized evolution. It's just a small deformation. And there is a picture. You deform a little bit. You apply the flow of the linearized system, and you deform it in the other direction. So it says that the evolution near hyperbolic fixed point is very close to the linearized evolution. This is a theorem. This is true for hyperbolic. So it means if you look at, where should I start? I should start here. Let's say this is the evolution by phi, right? Or maybe I don't even have to go through the origin. So let me look at one trajectory near. So I look at one trajectory, one evolution of a x close to 0. Then it says, oh, this evolution, you can get it as you go to this space. Here you apply, I'm going to cheat, but I'm going to say that this, the evolution by the linear system is just a line. So it's a simpler evolution in a sense. You apply this one, and then you go back. So yeah, this is a good picture. this evolution is given by, you go here, you look at the evolution given by ETA, and then you come back and you get the yellow one. That's this statement. So it means if you very locally, your evolution is not, it's a continuous near zero. The evolution is a continuous deformation. Of the linearized evolution. That is theorem. I think it's quite interesting. So this is a stability around a fixed point. And again, the fact that I assume it's zero is it's not a big restriction. All right. And I need to assume FC1 because I'm taking the Jacobian matrix, so you need to differentiate once. So it's not so surprising. Do you have any question? The proof is not so difficult if somebody is interested, but you probably need calculus 2 at least. So I wouldn't recommend it for first year who haven't attended calculus 2. There is, before coming to periodic orbit, there is just one more definition or one remark I want to mention, because these are terms that we can see at some places. So it's still about fixed points. If we consider x1 and x2, two fixed points, and we had an example like this in chapter 2, in previous chapter in 2 dimension, two fixed points. And let gamma of x be an orbit so that it converges backward in time to one of them and forward in time to the other one. So what is a picture? What is a picture? We have two fixed points, and we have one orbit between them, and we assume that this is x1, x2. So it means the evolution on the orbit is like this. If we go back in time, we are close to x1. If we go forward in time, we reach x2. So that's the idea. And I just want to mention two names. If x1 is different from x2, this orbit, I don't know where this name comes from, is called heteroclinic. This is a word that we see sometimes. And if x1 is equal to x2, so I need to change the picture, but we have an example again in 2 dimension. So if we are in this setting here, that the orbit start at x1 but go back to x1, we say that the orbit is homoclinic. I wanted to mention these two names. That's it. They appear when we study some dynamical system. Okay, so we can start. I will not be able to finish, but we can start now the analysis toward or around a periodic orbit. So let me, Or is there first any question? So what is the framework we will deal with? So we still consider, I'm always in this setting, an equation of the form x dot of t is equal to f of x of t. I will assume f c1 of m with value in Rn. M is a subset of Rn. And I denote by phi the flow, always the same thing. And I'm going to consider, I consider now a periodic orbit. So I consider gamma, it's a letter I haven't used, a periodic orbit. So what does it mean, a periodic orbit? So it means there exists a time t bigger than 0, so that if you look at the flow of t plus t on x, it's going to be back at the same point, phi of tx, for any point in gamma. That's the periodic definition of a periodic orbit. So it means this is true for any x inside gamma. So this is my gamma. And if I start here, this is the x. I let the flow after time capital T, I'm back to the same point. This is a periodic orbit. And at the same time, of course, if you start at a different point. If I start here, after capital T, I'm back to this point. This is a capital. This is a capital T, or this is a period. So I'm going to fix a certain point. I'm going to call this x0. And I'm going to so this is now, we are in Rn, but this is just a curve in Rn. And I'm going to consider a hyperplane. So what is a hyperplane? We are in R3. Look, we have one vector which is tangent to the curve. So we have this curve. At x0, we have one vector which is tangent. And then I take the hyperplane which is perpendicular. So this is called sigma, the hyperplane. I will even write an equation for this hyperplane later. The hyperplane perpendicular to gamma at x0. So you fix a vector which is a tangent vector to the curve, and you take the plane which is of dimension. This is of dimension n-1. Why? Because you have one fixed direction, so all the one perpendicular to it generate a plane of dimension n-1. And what we are going to look at next time, so this is my x0. I'm going to take a point on this hyperplane, which is not on the curve. And I will check and look if I let it evolve, if I obtain this. And you can immediately see why it's interesting. Because if we are in this case, it will probably mean that if I go on, it will go even further away. Why? Of course, this is just a picture. We need to make it more precise. While if we are in the different situation where you start at this point and you approach the curve, you may think that we are going to converge to this periodic curve. So this is what we are going to do. We take this surface perpendicular to the curve, and we study the evolution of points from it. By the way, it may happen that we never cross this surface again. It may happen that we go far away from it. Of course, I cannot cross another trajectory. But so this is going to be defined only if we come back and cross this surface again. So this is what we are going to define next week. It's called the Poincaré map. Maybe you have seen this word, Poincaré. So I will define it next week. And if we study this, and we will use some notion that we have studied in the periodic setting of chapter 2.8, if I don't do a mistake, we will be able to say something about the stability of this periodic orbit. So that's the first part of next week. Okay, any question or remark?